All right. Good day. Good morning. I realized that I was not able to finish our discussion actually for topic two. So I just want to make this supplementary video in case you guys still don't know how to do this, right? Because it appears that like no one is asking, no one asked questions about this earlier. So I was assuming you guys already know how to do it. But in case not, right? In the case that you guys are still unable to do this kind of thing, here we go with problem 2.6. What is the specific enthalpy H of refrigerant 22 at 2 bar and negative 25.18 degrees Celsius? So you might be wondering, right? From the get-go, it seems that one of these quantities is very exact. This thing, right? Why is it like, why are there so many decimal places, right? This one is very, very round, very table friendly, right? Meanwhile, this thing is not. So we have no other choice but to just go with the pressure table and see what happens with 2 bar, right? See what happens with 2 bar. So we'll go here now and we'll go to R22. So that will be later down here. So table A6. Table A7 is the temperature table. So table A8, we will have our pressure table. So this is R22 2 bar. Apparently, it is not higher or lower. The temperature is exactly, right? The saturation temperature here is exactly negative 25.18. That is why, right? That is why we are seeing this weird exact value. And so now, what is the specific enthalpy here? You might say to yourself, okay, I can see three different values: HF, HFG, and HG, right? Saturated liquid, something called evap, and saturated vapor. So in this case, this question is actually wrong, right? This question here is wrong. Why is that? Because we did not specify, or the question did not specify what the state or what the quality of this saturated fluid was, right? And so now we'll clarify that with this quality in saturated substances. So I will give you guys a formula, right? But in this case, this has to come from what we know so far, right? And this one, hopefully, this is commonsensical, right? This has common sense baked into it, right? The total mass of your two-phase mixture is just the mass of your liquid and the mass of your vapor, literally, right? M is equal to MF plus mg, right? That makes sense for us. And the other part is that if we divide both sides by m, we will get this thing. MF over m plus mg over m is equal to 1. In this case, this is the amount of liquid relative to the total, which is moisture. And this thing, right, is the amount of vapor relative to the total, which is your quality. So this thing, x plus y, is again equal to 1. Okay, so we'll think about these for later, but for now, right, we'll think of properties as well, right? Properties of two-phase mixtures, I am referring here to 4, right? V, U, H, and S. So that's volume, internal energy, enthalpy, and entropy. The total property of your two-phase mixture is just the combination, or right, the addition of the contribution of the liquid phase and the contribution of the vapor phase. Say, for example, the total volume of your fluid is just the volume of your fluid, the volume of your liquid, right? And the volume of your vapor, which makes tons of sense, right? In this case, say for example, for internal energy, that literally the total energy of everything is just the energy that is contributed by the liquid and the energy, the internal energy that is contributed by your vapor, which makes sense, right? So now you might be saying, okay, why are you writing this in capital letters? Because there is an important distinction between extensive and specific properties. Why does it only apply, right? Or notice that it only applies to V, U, H, and S, which just so happens to be the things that you can get, the properties that you can get from the steam tables, from the property tables. And so, if you remember, the extensive property is equal to the mass times the specific property, or more simply, big number, right? Big letter pala rather, right? Is equal to mass times small letter. Big letter, mass times small letter. Big letter, mass times small letter. That kind of thing. Okay? And so now we'll put all of this together. We will have this, something that we've seen earlier, and this, something that we'll see, right? We just have seen. And if you're wondering what is n in this situation, I'm just using n as a replacement for the four possible values here, four possible properties here, V, U, H, and S. And what we're going to do is now, because they are big letters, we will now split them up into their corresponding specific properties. This, right? From here, you will get this, right? Hopefully, we understand that big N is equal to M times small n, right? And you might be wondering, why is NF, why does it only correspond to MF? Well, the mass of the liquid is the thing that is contributing to the property of the liquid portion. Same goes with the mg and ng. And now what we will do is we will divide both sides by m. What will happen is this, right? And again, hopefully we can draw the conclusion here that, wait a second, I've seen this before. This is supposed to be my moisture, and this thing is supposed to be my quality. This thing. Right? We're almost there, right? The only thing left now is for us to simplify things a little bit, right? Earlier, we told ourselves that x plus y is equal to 1. In reality, right, there are not a lot of stuff, there's not a lot of stuff, or there are not a lot of computations that deal with y specifically. In this case, or in most cases, y is just omitted. Why? Because you can very easily just replace y with 1 minus x, right? If you move the x to the other side, then you will get this, right? Finally, what we will do is we will expand nf minus x times nf plus x times ng. And what you will see is that these two terms in here have a common factor of x. And at that point, we will arrive at our equation, right? Our formula, right? This n, right? You can replace this with anything from V, from U, from H, all the way to S, right? You can replace this with those four properties. And therefore, we will have four versions of the same thing. Hopefully, this is not taxing for you guys. V, U, H, and S, right? They are literally just the same thing. Right? All of them are the same thing. And now, you notice that there is something in here that is highlighted in purple, right? Hg minus Hf, you can replace that with Hfg. This is a special thing that holds special places in steam tables because this is what we call the latent heat of, right? Latent heat of vaporization, right? This is basically the amount of heat that you would need to give to a saturated liquid, to a liquid that is ready to boil or ready to evaporate, for it to fully evaporate, right? For water, right? For water at 100 degrees Celsius, the HFG is 2257 kilojoules per kilogram. Why do I know this? Well, ask me when you are fourth year, right? But you will have to know this because actually third year, as early as third year, this will be used because this is the amount of energy per kilogram that you need to supply water so that it can fully evaporate, right? Okay. And basically, this is also available in your enthalpy charts or tables, right? Here, the latent heat of evaporation or vaporization is also given here. So, as you can see, HFG is just Hg minus HF, right? And if you're wondering still how that is possible, right? Say, for example, a liquid is already ready to evaporate. So that means it has an energy of HF, right? It has an enthalpy of HF. As you can see, I'm like interchanging energy and enthalpy already. If you're a little bit confused, hold on to that confusion. We will address that in the next few topics. But say, for example, it's already in this state, right? It's already saturated liquid. What will you add to it? You're supposed to add your HFG. What is HFG? HFG is just Hg minus HF. So what happens is that you cancel, you will have Hg. So from here, you got here. So you have fully evaporated. Now it is a saturated vapor, right? So this is a special kind of thing for H, right? As you can see, it's the only one with 3 entries, right? But technically everything has a VFG, has a UFG, has an SFG. It's just not used as often, right? And if you want, you can check it to see that I am not lying, right? 246.77 minus 35.34 is going to be 211.42. And so now, we go back to our original question, right? Our problem 2.6, I will now revise it. And I will say, what is the specific enthalpy of refrigerant 22 vapor? Now we understand, okay. You specify that this is all vapor because this is just vapor we're talking about. That means that this is a saturated vapor. Now I know what the answer is supposed to be. It's supposed to be 239.88, aka, right, this thing, the Hg, right, the Hg of this entry at 2 bar. Okay, now we'll revise the question just a little bit more, right, and we will say, what if it were not just completely vapor? What would be the specific volume if the fluid had a quality of 0.85%? Okay, so we'll just apply the same thing to what has happened earlier, right? 2.6a, right? We are now going to have refrigerant 22, right, at a pressure of 2 bar and a temperature of negative 25.18. Now, the thing about this is that this tells us that this is in a saturated state, right? This tells us that this is in a saturated state. And moreover, they did specify that our quality is supposed to be 0.85. I'll write this down in 4 decimal places so that we are provided much more accuracy, I suppose. And, well, I'll make it standard, but in case, right, I'll write down in the problems that I want the quality in 4 decimal places. But please make this a standard also for you, right? This is 4 decimal places. And, well, we can just put it in our solution that we just want the V, right? What we want in here is the V. So from our tables, right? From what table is this again? From table A8. Yeah, table A8. Right? Our value for VF is, what is our value for VF? It's 0.7340. 0.7340 meter cube per kilogram. And then our VG is going to be, what is our VG? 0.1123. 0.1123 meter cube per kilogram. So basically what is happening is this. A visual representation of this is something, is something like this. Say, for example, let's change the color here. VF and then VG. Right? This is your value of VF. And then your value of VG is here. Say, for example, your VF in here is 0.7340. And then your VG in here is 0.1123. Now, please, right? I've already committed a mistake. Please look at your steam tables very closely, right? If you're to write this down, this would already be wrong. Why is this wrong, right? What you would see in here is that, wait a second, this is bigger than this. There's usually no problem with that. It's just that now you have to be a bit more curious as to why that is the case, right? In linear interpolation problems, that's no big deal, right? It doesn't matter if something is smaller than the other. That is why we have the corresponding note, right? Whenever we're looking at mid minus small over big minus small, you always have to look on the other side, the corresponding value, not the numerical value. right? So we are equipped for that kind of thing. It's just that now your VF has a special note. If you remember, specific volume is the reciprocal of density. Which thing is denser, liquid or vapor, right? That would be liquid. That means that if you take the reciprocals of both, the specific volume of a liquid would be much lower than that of a vapor. Say for example, right, we'll just list two different things, like the water, right? Liquid water is 1,000 kilograms per meter cubed, and the air is like 1.2, right? If we take their reciprocals, you would get in here 0.001, right? Meter cube per kilogram. On the other hand, for air, it's just going to be 0.833. Look at that, right? I know these are not the same substance, but still, just to get a little bit of how should I say this? A little bit of perspective, right? Liquids should have lower, right, specific volumes than gases or vapors. And so now, why is this the case? This is because if you're going to look at the saturated liquid, it's not displaying you the value of VF. It's displaying you the value of VF times 10 raised to 3 or times 1,000. This thing, or rather this 0.6847 is actually VF times 10 raised to 3. So for you to get the value, the correct value of VF, you need to divide this small thing by 1,000, right? And as you can see, that makes more sense because now look at this. This thing is bigger than this. This thing is bigger than this. That's not possible, right? Or that won't make sense. I mean, it's possible, but it will not make sense. But now look at this, right? 0.75 and then 0.07, it gets even smaller. So in this case, what is happening, right? It would make sense. And plus, hopefully, right, you are reading the entirety of the table because, right, say for example, you are now reading the table physically. Just look down, right? You will see in here a little note, very helpful note, right, that your VF should actually be divided by 1,000. Okay, so hopefully no one trips up with this, right? No one gets tripped up by this thing, right? Of course, I will test you guys on your retention of this. This should be divided by 1,000. So that means in this case, this is actually going to be 1, 2, 3. This is going to be 0.0007340, right? Let's remedy this. 0.7340 divided by 1,000. And so what would happen is that this thing corresponds to a quality of 0%. This thing, on the other hand, is at 100%, right? What would be the value of your specific volume if now it would reach 85%? This is now what we are asking. So honestly, there are multiple possible solutions for this, but I can see two that would make a lot of sense, right? At 0, your V, right, would be VF, right? It's in saturated liquid. Therefore, this value would be at 0.0007340. So that is quite small, right? And at 1, aka 100%, it would now be at 0.1123. Now the question is, right, at quality of 0.85, what would be the value of your specific volume, right? You can put this as a linear interpolation problem, or we do the thing that we just discovered earlier, which was V is equal to VF plus X times VG minus VF. Okay, let's just put this together. 0.7340 divided by 1,000 plus 0.85 times VG is 0.1123 minus 0.7340 all over 1,000. And the answer here would be, if I remember correctly, 0.0956. I remember it because it sounds like a phone number. Meter cube per kilogram. Okay, this is our answer for letter V. right? For the letter V for, what do you call this? For specific volume. Now, before the video ends, I would like to teach you that there is actually an approximation. An approximation like this. If you look at this, right? And if you say to yourself, wait a second, this is really small. Yes, we understand that it's small, but look, if we were to truncate this, that is really small, right? If we're now looking at both things in terms of 4 decimal places, that is really small. If I truncate or if I round off, what will happen is something like this. And like this. And if I round off even further, this is just 0, right? So what a lot of people do, right, when they're talking about VF as a value, right, when you're approximating, when you don't have the time, right, they just say that this is approximately 0. And so that makes things a whole lot easier, because now, look at this. Cancel. Your V, your value of specific volume is just literally X times of approximately equal to X times your VG. That's it, right? And if you do this, right, please don't do this often. This hurts, right? 0.85 times 0.1123, that will give you 0.0955, which is still quite close, right? It's not as close as I would hope it does, but it is still quite close. So that is something that you might want to do, maybe if you're running out of time, right? That is something that you want to do. And so, just to wrap things up very neatly in a bow, right? Our answer is this, yep, 0956. To wrap things up quite nicely, here is a question that looks a lot like your diagnostic assessment. Through unwilling measurements, 2 lazy scientists have obtained the following data. At 15 degrees Celsius, the minimum energy a device holds is 1,250 kilojoules, while the maximum is 2,600. At 20 degrees Celsius, the minimum energy is 1,750 kilojoules, while the maximum is now only 2,850 kilojoules. Now the question is, they need to know how much energy the device holds at 65% capacity while its temperature is at 18 degrees. What is the simplest approximation? And the answer, if you want to do this, go ahead, right? But this is a classic triple interpolation problem or a bilinear interpolation problem. And the answer here, if you want to try it out, give it a try for yourself, right, would be 2,330 kilojoules, right? You can try this out either both ways, right? Try doing the vertical thing first, try doing the horizontal thing next, just so you arrive at the same answer. Okay? So that's it. Thank you very much. I'm so sorry I did not remember this properly, but I hope you guys did learn something from that video. Okay? Thank you.